Our next speaker, and he will talk about stabilization of linear time-varying reduced order models, a feedback controller approach. Please go ahead.
So hi everyone, I'm Rambod Mujgani, now a postdoc at Rice University, but this work is part of my PhD dissertation done at UIUC under Maciej Blajewicz. Since then he has moved to the incorporation side of the world, and I'm happy to be here. I often don't get the opportunity of talk about this side of my work in my PhD, so glad to have this opportunity. So often we have our governing equation, we can solve them, discretize them, and solve them to the accuracy that we are looking for using traditional approaches. But for many of the applications, such as control, real-time calculation, or many query applications such as optimization or uncertainty quantification, we need to have reduced order models or some surrogate models that can deliver the solution at the fraction of the cost of these high fidelity simulations. So one of the approaches that are often used and is based on the physics of the problem and some mathematical projection is projection-based reduced order modeling. The underlying assumption on projection-based reduced order modeling is that the solution is compressible. That means if we solve our PDEs, the solution lies on a manifold of significantly lower dimension. Then the second assumption is that we can learn these manifolds. We can identify them using the training simulation and snapshots we gather. And then we can reformulate our governing equation with respect to this newly learned manifold. And hence we are going to have the reduced order model that can deliver the cost at the fraction of the cost of the original governing equations. So let me brief through the steps of this reduced order modeling. Consider the discretized system, the residual system of the state parameter W at time n, so it's equal to 0. We project that onto the global trial subspace, so W, our state parameter at each time step n, it is approximated on this lower dimensional space by a linear combination of our bases and representation of the solution on this manifold WR. And k is assumed to be much smaller than the n, the size of this state variable, so that's the reduction or compression part. Then finally, we project this residual approximated on the trial subspace onto the global subspace of U again by U transpose R, and we are going to end up with equation 3, which is of lower size compared to the equation 1. But if you pay attention, nowhere in this procedure we talked about the stability of this system, and there is no guarantee on the stability or energy preserving characteristics of equation 3. So for that, and this is a known problems. We can have high fidelity models. Here I have shown a Riemann 2D Riemann problem that is stable, but we perform POD on it. We project that on the POD subspace. We run the simulation, and the simulation on the POD subspace is going to blow up. So we need to have some approach to address the stability issue, and this stability of the ROM or stabilization of the ROM can be categorized into two major approaches. The one is a priori stability preserving model order reduction, such as balanced truncation or energy-based projections. This ensures that the ROM that we are going to end up with are a priori stable. The other approach is going to be to stabilizing these reduced order models. So that would include addition of the closure terms or use of controllers on the reduced order models for the purpose of making sure that the reduced order model is stable, not for the controlling the system. The first set of approach, the priori stability preserving approaches, have their own challenges, like the balanced truncation scales with the size of the high fidelity models that can be size of millions if you are working with a fluid dynamic system, which is intractable. The energy-based projections are limited to the specific system that they have been developed on. And so that's one issue. A posteriori stabilizing ROMs approaches are more versatile. So our goal here is to stabilize linear time varying reduced order models a posteriori. And we are interested in the time varying ROMs. We can have time varying ROMs coming from two major sources. The system itself can be time varying, the high fidelity model can be time varying system, or the basis on which we are constructing our ROMs can be time varying. So these are the main two motivations and application of the problems. For that, we are going to extend the eigenvalue stabilization of time invariant ROMs by Klashenkova to linear time varying systems. So in this work, they reassign the eigenvalues of the system metrics to ensure stability. We are going to use a similar approach, but the stability constraint and the challenge are a bit different on the time varying ROMs. So if you remember this equation, that was my reduced order model on the test subspace. Uh, if I want to reframe it for the linear time varying system, it's going to look like this. My A is time varying, my bases are constant in time, but then if you look at this term, it's going to be a reduced order system matrix, which is time varying. For the second case, I can have my bases time varying. In the traditional POD subspace, I have my basis U constant, but then there are cases that we are interested in having a time varying basis. And we specifically got interested in this problem because of this work, low rank registration based manifold for convection dominated PDEs, where we developed an approach to make POD efficient for convection problems, and that is by identifying in this time varying grid. I won't go through the details of that, but the end result is that we are going to have basis which is constant on this time varying grid, but for our equations, we need to interpolate back, project that back that basis on our time constant grid, and that leads to a time varying basis. So I'm going to have, in the general case, if we have our residual matrix, now our bases are time varying, and again I end up with the same time varying reduced order model. To introduce some nomenclature, consider this time discrete linear time varying system W at the next time step is equal to system matrix multiplied by the state matrix. I have the controller and observation here. We know the solution of this problem. It is the transition matrix between the time step that we are interested in and time zero, initial condition and convolution of the transition matrix and the controller, where the transition matrix is consecutive multiplication of the state systems matrix. For this to be stable, we need to have norm of this transition matrix to be bounded. So there exists a C, a bounded value, which norm of this transition matrix is less than that, is equal to that. And to develop our controller, I'm going to use this theorem. We know that for a time varying system, the ratio between the norm of the state variable at the time step that I'm interested in over the time step 0 is bounded by eigenvalues of multiplication of the eigenvalues of A transpose A, or in other words, with the singular value of my system matrices. So that means if I can control my singular values, I can control my ROM. And by control, I mean I can modify my singular values in a way to make sure that the system, the ROM, is stable. So if I go to the ROM equations, I add a controller to that, BCUC, to the whole equation. I assume my controller comes from a gain from the state variable on the reduced space. I add that to equation 16 and I end up with equation 17. I call this now my stabilized reduced order system matrix. So A hat R. Uh, and I propose this controller type. I'm going to choose my B matrix as a left singular values of my state system, and I choose my gain as sigma V transpose. And if I put this back into my equations, I can reformulate my system matrix R stabilized as a modification of the singular values of that system matrix. But this doesn't control my system the way I want it, so I need to have it enforce the trajectory of the system. And for that, I'm going to be minimizing the distance between the high fidelity model, the solution, the observation from high fidelity model, and observation from my reduced order model. And I'm minimizing over sigma, so the singular values of my state matrices. Uh, and singular values are positive, so I have that as my constraint, and also I add the stability constraint into my minimization problem. So this problem now scales with the size of the ROM, but not the high fidelity model, so it is more advanced, more tractable compared to the balanced truncation methods, but also we can improve this on it. When using that theorem that I just taught, it makes sense to only control the largest singular values of the system, so I can have that. Also, it happens so that we don't need to control all of the system matrices. I can intermittently control some of my matrices. So we have applied that to a mechanical vibration problem. Here, some of the system parameters, some of the springs and dampers are time varying. Here I have the signal that shows my time variation. If I perform high fidelity model, I get this solution. But if I perform Cryer-Ram for this, the system becomes unstable and low in accuracy. So I perform my stabilization method with by controlling 3 of the singular values intermittently every 10 or every 100 time step, and I get this red output of the system or black output of the system respectively. But this choice of delta n, the intermittency that I am controlling my system and singular values, are hyperparameters of my minimization problem. So as any other hyperparameter selection, I have formed this error versus hyperparameter graph, and as usual, the usual suspect, I choose the elbow of this L curve as a compromise between the accuracy that I'm looking for and the cost of my control. So the system is going to be controlled to be stable at this point, but what happens if I change my input? I can empirically show that the accuracy of the system versus the standard deviation of the noise I'm going to have. So I've plotted the Cryer-Ram error versus the stabilized Ram error. You see for lower values of the standard deviation of the noise, my stabilized Ram is much more accurate compared to the Cryer-Ram. So these dots small here are different samplings from this normal distribution as the noise for my input. I increase this standard deviation, and as this increases, the accuracy of the stabilized ROMs decreases in some of the cases, and this red dots showed that in the cases that the stabilized ROM are less accurate compared to the Cryer-Rams. And of course, when I increase that, I see more of these red cases. But in general, if I plot the error of this stabilized ROM, this red and this and the Cryer-Ram in this blue line, I see in most cases I can even improve accuracy, especially in lower noise bounds. But going back to the second type of the linear time varying ROMs, I'm going to look at the wave equation on the grid that is time varying. So on the left I have the Eulerian grid, and on the right I have my time varying grid. So the basis on this grid is going to be constant, but my ROMs, because I want to interpolate that to the Eulerian grid, is going to be time varying. and the solution looks like this. So if you compare figure B to A, you see the advantage of using this time varying bases and why we are interested to make sure these kind of ROMs are stable. I have plotted error versus time in this graph. The error goes up, but since this system is unstable, the error jumps after the first time period, and that's clear from looking at the eigenvalues of the Monroe matrix. If I now run my stabilization, I'm going to move the eigenvalues of this Monroe matrix within the unit circle, and my ROM eventually is going to be stable at the cost of losing some accuracy in this phase, but at least I can have more accurate predictions in time. So today I showed you that many of the reduced order models are not inherently stable. We came up with a feedback controller approach to stabilize LTV ROMs. I showed an example for LTP, linear time periodic system, but you can use the same approach for LTI systems as well. Also, this can be applied to different type of ROMs, so it's an non-intrusive approach, and can be applied to any ROMs regardless of where they are coming from. And the dimension of the controller does not scale with the size of the high fidelity model. It scales with the dimension of the ROM or fraction of that by using only the first largest singular values of the state matrix. And this controller can be activated intermittently. This is published in the journal, so you can go for more details in this place. And with that, I'll take any questions.
Thanks a lot. I think the results look really impressive. So while we wait and see if there's something coming up in the Q&A, I would like to ask the first question. So I'm interested in adaptive ROMs, and it seems your method applies in that case. One thing that I'm a little bit surprised of is it doesn't seem it shows up how you adapt the bases. So is your stabilization agnostic to the way I choose the next basis?
Yeah, so as I tried to discuss here, when I have my system matrices, I don't have access to my bases. I just change this my system matrices at this reduced form, and I just do my control on the reduced form and not on the basis.
Okay.
So going from this to the basis is actually a good question because we eventually want to know about the basis, but I'm not sure how to do that yet. And
Yeah,
I haven't looked at that problem, so yeah.
and to change the way one adapts the basis so that it gets easier to stabilize or something like this.
Yeah.
Okay,
So
interesting.
for my problem, I was looking at some point to my problem, I mean my registration problem, to have this stability constraint as a constraint on my optimization, but I had issues with convergence of that optimization. I didn't spend too much time solving those issues. But that makes sense to have the constraint on that procedure that we are coming up with the uh, basis, type of the
Yeah,
basis.
yeah.
Yeah.
All right, thank you. I don't see any other questions, comments. All right, then thanks again for the presentation. So this